All right, so the law of definite proportions, it seems like we've already talked about this earlier in the year, way back at the beginning, maybe Unit 2, when we talked about the discoveries that John Dalton made. One of them was the law of definite proportions, and that says that masses of elements are always in the same proportions in a compound. So let's pick, let's pick some water. Okay. So the ratio of hydrogen molecule or hydrogen atoms to oxygen atoms in water is always what to what? 2 to 1. So if you were to sample this compound based on what we talked about earlier with the mass of the hydrogen being 1.0 something and the oxygen being 16, basically, if you had 18 grams of this, how many grams of it would be hydrogen and how many grams would be oxygen if you had 18 grams of water? Yeah, it'd be 2 to 16. And that would be the ratio you would say, or you could even say 1 to 8. So that would be the ratio of the masses, or we're talking about masses here. That would be the constant for all samples of water. Is you would have a 1 to 8 ratio of the mass of hydrogen to the mass of oxygen. And that's the kind of experimentation that John Dalton did, is he would get things and he would compounds and he would break them down into their elements and measure the mass of each element that he collected from that and would determine stuff like this. Another one that you might encounter may be carbon monoxide. And let's see, carbon monoxide, the carbon's 12, the oxygen's 16. So you would expect a ratio of 12 to 16, or you could simplify that. Simplify. Yeah, 3 to 4. Yeah. So you'd expect a 3 to 4 ratio of the mass of carbon to the mass of oxygen in the compound. And it doesn't matter if you have a small sample of carbon monoxide or a large sample of carbon monoxide. This is going to be consistent. There's also another law that comes out. It's the law of multiple proportions, and that says that same two elements can sometimes form more than one compound as long as they're present in different ratios. So, what's the other compound you can form with carbon and oxygen? CO2. Yeah, sure. So that one's going to be present instead of a 12 to 16. That would be present in a 12 to 32 ratio. And I'm going to factor it. I bet I can figure it out if I factor it. So 2 times 2 times 3. And that one's going to be, let's see, 8 times 4, right? So that would be 2 to the 5th power, basically. 2 times 2 times 2 times 2. Okay, so a couple of the 2's cancel out, so it would be a 3 to 8 ratio. Which makes sense because we doubled the amount of oxygen. So the carbon monoxide has a 3 to 4 mass ratio of carbon to oxygen. The carbon dioxide would have a 3 to 8 ratio of carbon dioxide. So they have different ratios or different percentages of each element in them, and that makes them different compounds. All right, another thing that so we'll come back to some of this later when we do percent composition and empirical formula stuff. All right, conversion factor. Do you remember doing that back with the dimensional analysis stuff? Kinda. Okay, so it's going to come back to us. One of the most important conversion factors that we're going to use here is the mole equals 6.02 times 10 to the 23rd particles. Now, I said representative particles here. What are some of the particles that we have talked about so far in chemistry class?
That's a great question.
That is a great question. What are some of the things that you might want to count? Like the carbon and the oxygen, they are both what? They are both nonmetals. I heard that one, but that's not what I'm going. Um, Type of particle that we're talking about here. They're atoms. Yeah. So we could count atoms. If you have atoms that are combined together, you could count atoms that are covalently bonded to one another make. Yes. Yes. And if you have a covalently bonded compound, it exists in things that we call, it starts with an M. Molecules, yes. If it's an ionic compound, we don't say molecules, we say formula units. Um, hmm. Oh, there's other stuff, and there's one or two more things we could list there. You actually could say particles. Yeah, I'll come back to that if I think of anything else. All right. So Avogadro's number is the number of, here it is, ions. That's another one. Okay. Avogadro's number is the number of particles in a mole. And we watched those videos and they told us about, all the if real life examples of this. So that's a lot of particles in every single thing. Okay, so molar mass is the mass of 1 mole of a compound, and units there are going to be grams per mole, or sometimes expressed as AMUs, and those are equivalent to each other for all practical purposes in here, because you would add them up the same way from the periodic table. So let's look at the water. So for the water, we would add up the 2 hydrogens, give the mass from the periodic table, and the 1 oxygen. And when you add those up, let me get an actual calculator. I'll be specific. All right, so 2 times 1.008 plus 15.9994, you get 18.01. 5, so 18.02. Usually 3 or 4 significant figures will be enough for the conversions that you need to do. All right, let's talk. We'll come back to this and do the equality and possible conversions there. We'll do that in just a moment. Let's talk the sodium chloride. So how many sodiums and how many chlorides? 1 of each, right? So when we look at the periodic table, find the mass of sodium. Mass of sodium is, so I'm going to round off there at 4 significant figures. Chlorine is 35.45. All right, you add those together, and it comes out at 58 point something. 58.44. All right, and then another compound, just to be aggravating, is the copper chlorite, copper 2 chlorite, give it the correct name. So here's the copper, 63 point, what is it? 55. Now, this is kind of tricky. Okay, there's parentheses, and then inside, or what does the 2 outside of the parentheses tell me? There's 2 of everything inside the parentheses, right? So there's how many chlorines total? 2, and how many oxygens total? 4, right. So we'll do 2 times the chlorine, and then 4 times the oxygen. And let's add those up. 63 3.55 and 2 times 35.45 and 4 times 15.9994. And that'll give you a grand total, at least I got 198.4. Yeah, I'll just stop there. Okay, grams per mole. That's 4 significant figures, so that should be enough. Now, the equality here is, I wish I hadn't written that line down. All right, so what this is saying is that 1 mole of water equals 18 grams, or 18.02 grams. 1 mole of sodium chloride equals anybody? 58.44. And 1 mole of copper 2 chloride equals 198 point. Are y'all just like not saying it because you know, or are you not saying it because you have no clue? Or are we just bored out of our minds? Where are we at? I'm trying to catch up. Damien's bored out of his mind. Okay. You're trying to catch up. Okay. Can
you zoom in a bit?
I can try. Is that better?
Yeah.
How confident do y'all feel that you could add up molar masses on your own now? Okay. Yeah. Okay. Yep. To make conversions of this, we can do one of the two things. We can say put 1 mole of water over 18.02 grams, or we can do the opposite. Put the 18 grams Now, if you do the one with the grams on the bottom, what unit are you trying to cancel out? Like, what would you have in front of this in the train tracks if you're putting grams on the bottom here? You're trying to cancel out grams, right? And this one you'd use if you were trying to cancel out moles. Same thing here. You could put the 1 mole of sodium chloride over the 58.44 grams of sodium chloride, or you could do the grams over the moles. And same with the copper 2 chloride. All right, so this should have you set up now where you can do worksheet 1 in the packet. And for the last few minutes of class, I'm going to give you